Welcome back to the Deep Dive. We're the show that digs into the research, the reports, the really dense stuff, so you don't have to, getting you up to speed fast. Today, we're jumping into a future that, well, it's happening right now, isn't it? A world where AI isn't just some tool you point and click. No, it's an active, autonomous partner. It's involved in critical operations. Just imagine for a second an AI managing a whole city's smart grid, automatically rerouting power during an outage. Or maybe an AI legal assistant, drafting briefs completely on its own, maybe even negotiating settlements based on live court data. Now, these aren't like distant sci-fi dreams anymore. We're getting closer to this stuff every single day. But as these AI agents get more capable, more autonomous, take on these really critical tasks, a fundamental question pops up. How do we keep them secure? How do we make sure these powerful, self-directed systems don't get hacked or manipulated or, worst case, just go completely off the rails? Okay, let's unpack this. Today's deep dive is all about agentic AI threat modeling. That's the focus. And specifically, we're looking at a really interesting novel framework called Maestro. Now, when we say agentic AI, what do we mean in simple terms? Well, we're talking about AI systems that can, learn on their own. They can make decisions. They can act autonomously within some environment. And crucially, they often interact with other systems, maybe other software or increasingly other AI agents too. So this isn't just your average chatbot generating text. This is about systems that can perceive their surroundings, they can reason, and they can act to achieve goals, sometimes in ways that weren't explicitly programmed beforehand. Now, traditional security frameworks, they were pretty good for traditional software, right? Software that behaves predictably based on its code. But agentic AI, it introduces a whole new ballgame. It's autonomy, the way it learns dynamically, its ability to interact and evolve. It just means we need a fundamentally different way to think about securing it.
Right, exactly. And what's fascinating here, and really why Maestro is so important, is how it gives us a structured, kind of holistic way to look at something that's incredibly complex. Maestro, that stands for multi-agent environment, security, threat, risk, and outcome. It's really designed for the people on the front lines. The security engineers, the AI researchers, the developers building and deploying these things. So our mission, let's say, in this deep dive is to help you understand exactly how Maestro lets you proactively identify, then assess, and finally mitigate risks across the entire AI lifecycle, not just at the end, but all the way through. The goal, ultimately, is to enable you, the listener, to build robust, secure, trustworthy, agentic AI systems you can actually rely on. And it does this using this structured, layered approach that really moves beyond those traditional methods we just mentioned. It helps us understand vulnerabilities not just in isolation at each layer of the architecture, but maybe even more importantly, how those layers interact, how vulnerabilities can actually cascade, jump from one layer to another. It's about shifting from being reactive to being genuinely proactive.
That proactive layered approach sounds incredibly promising. It makes a lot of sense. But before we, fully unwrap Austro and dig into its architecture, let's set the stage properly. We probably need to take a quick but thorough look at some of those familiar faces in the threat modeling world. The traditional ones, let's examine their core ideas and then critically see how they stack up against these unique, sometimes kind of unsettling challenges of agentic AI. Because understanding where they fall short, where their limitations are, that's absolutely key to appreciating why Austro isn't just like a small improvement, but a really critical foundational shift for AI security.
Absolutely. It's crucial context. When we talk about traditional threat modeling, there are several frameworks that have been staples for years, and for good reason. They work well in their intended domains. You got, for instance, Stride. That's a classic, came out of Microsoft. Often used for general security threat modeling. It covers things like spoofing, tampering, repudiation, information disclosure, denial of service, and elevation privilege. It's kind of a fundamental checklist. Then there's PASTA. That's the process for attack simulation and threat analysis. It takes a more risk-centric view, really emphasizing the attacker's perspective and the business impact of potential threats. After that, Line Dean. This one stands out because it's specifically designed for privacy threats. It gives you a systematic way to categorize and analyze risks to privacy, which is obviously huge with AI. Then you have Oxtave, that's operationally critical threat, asset, and vulnerability evaluation. It's more of an organizational risk management framework. Helps companies figure out what their critical assets are and build security strategies around protecting them. Trike is another one.
It focuses heavily on system modeling, using detailed requirements and implementation models. Tries to integrate risk assessment right into the design phase. And finally, there's VST, Visual, Agile, and Simple Threat Modeling. It emphasizes automation, integrating directly with modern development workflows. Pretty useful in, say, Agile environments. Now, while each of these frameworks has its strengths and a definite area where it shines, the critical point, as you said, is that none of them were originally designed with a unique, dynamic, often unpredictable nature of agentic AI in mind. That's the fundamental mismatch. And that's where the gaps really start to show.
That's a crucial distinction. Yeah, it really gets to the heart of the problem we're trying to solve here. Okay, so let's dig into each one a bit more. Understand their specific strengths, weaknesses, and most importantly, where and how they fall short when you try to apply them to agentic AI. We're basically asking, why can't we just tweak what we already have? Why do we need something completely new like Maestro?
That's a great question. And it's because the differences, well, they often run deeper than they might seem at first glance. Let's start with Stride. It really is a cornerstone in cybersecurity. Its categories spoofing, tampering, repudiation, info disclosure, denial of service, elevation of privilege, they're still relevant for identifying lots of common vulnerabilities. Its strengths, simplicity, broad applicability. It gives you a solid foundation for spotting typical security flaws, even things that might affect the infrastructure an AI agent runs on, like data tampering and storage, or a DOS attack against an API the agent uses. It's relatively straightforward to understand and apply. So it's a good first step for many, many software projects.
Right. So it's useful for the traditional software bits around the AI, but where does it specifically stumble when facing the agentic AI itself? Can you give an example? What kind of AI-specific threat would it just completely miss?
That's exactly where its limits become really clear. Stride just doesn't adequately cover the truly unique challenges that come with AI agents, especially the sophisticated nature of adversarial attacks, or the risks that stem from their, well, often unpredictable learning and autonomous decision-making. Take adversarial machine learning, for example. Stride doesn't have a specific category for attacks where inputs are deliberately crafted to fool an AI model into misclassifying something, even if the input looks totally normal to a human. Imagine a self-driving car as AI. It's fed an image of a road sign, but that sign has been subtly altered with tiny, almost invisible pixel changes. Stride might help you detect if the sign data was tampered with over the network, sure, but not if the image itself, though physically untouched, was designed specifically to evade the AI's detection or cause it to make the wrong decision. It also struggles to model the dynamic, autonomous behaviors of AI agents or the complex interactions you see in a multi-agent system. Those are central to agentic AI. So yeah, while Stride can offer some basic coverage, it's essentially missing an entire dimension of AI-specific vulnerabilities. It's just not built for that.
That makes perfect sense. It's like trying to use a standard wrench on a completely new type of bolt head. Okay, next up was Pasta. That one sounded a bit more involved, focusing on the attacker's view and risk.
Indeed. PASTA, the process for attack simulation and threat analysis, it's definitely a more sophisticated, risk-centric method. It really emphasizes understanding things from the attacker's viewpoint. It's a 7-stage process. Starts with defining objectives, goes through technical scope, application decomposition, threat analysis, vulnerability analysis, attack modeling, and finally ends with a comprehensive risk and impact analysis. Its strengths really lie in that risk-based approach. It's invaluable for prioritizing threats based on their potential business impact or mission impact. It pushes you to deeply analyze attacker motivations, their capabilities, their likely methods. This can lead to much more comprehensive and actionable threat models compared to just a simple checklist.
Okay, so it's robust on risk prioritization. But what about its limitations for AI specifically? Is it flexible enough for how quickly AI systems change and evolve?
That's precisely where its weaknesses start to bite. While it's powerful, PASTA is quite complex and resource-intensive. It demands significant expertise and time, more so than other frameworks. And, much like Stride, it fundamentally lacks detailed guidance on those AI-specific vulnerabilities. It's very involved. Stage gate process also means it might not be flexible or agile enough for the super-fast, iterative development cycles we see in AI, where models and capabilities are constantly being tweaked and updated. For AI specifically, PASTA doesn't inherently focus on threats like model extraction. Remember that, where an attacker steals the AI's underlying model by repeatedly querying its API. Imagine someone systematically querying a valuable commercial image recognition AI until they can basically reconstruct a working copy of the model itself.
Right, stealing the intellectual property.
Exactly, it's IP theft, and PASTA wouldn't have a neat category for that. It also struggles with the inherent complexities of autonomous AI decision-making or the downstream effects of data poisoning during the training phase, where malicious data is subtly injected to corrupt how the AI behaves later on. So while its risk-centric approach is definitely valuable, it needs careful, significant adaptation to really model AI agent behaviors and their specific risks. You might even need entirely new risk categories to properly address adversarial ML or the unintended consequences of AI just doing its own thing.
Privacy is obviously a massive concern with AI, especially with LLMs and agents churning through sensitive data. How does Lin Dun fit into this?
Lin Dun is unique here because it's laser-focused on privacy threats. It uses categories based on principles like linkability, identifiability, non-repudiation, detectability, disclosure of information, unawareness, and non-compliance. Its strengths for privacy are undeniable. It provides a really crucial, systematic way to identify and analyze privacy risks. And that's absolutely essential because AI agents often process or infer insights from personal data, leading to pretty significant privacy implications. It's excellent for figuring out how data could be linked back to an individual or disclosed when it shouldn't be.
Sounds super important for any AI handling personal information. But what about its gaps? Does it miss the broader security picture for agentic AI?
That's its main weakness in this context, yeah. Its narrow scope. Line du Day is primarily about privacy, which means it inherently overlooks other critical security threats common in agentic AI systems. It only partially considers how an AI making decisions autonomously might inadvertently impact privacy, which is a big oversight given how independent these systems can be. For instance, it wouldn't directly address threats like a denial of service attack aimed specifically at shutting down an AI's ability to make predictions, preventing it from working. Or model extraction, which, yes, can have privacy implications if the model reveals training data, but is fundamentally a security threat involving IP theft. It also doesn't really model the unique risks that come directly from the autonomy itself, like an agent deciding on its own to collect data it wasn't supposed to. So, while Lendone is absolutely essential for the privacy angle in agentic AI, you must pair it with other, broader security frameworks to get a truly complete threat model. And to make it more effective for AI, you'd probably want to add categories for machine learning-specific privacy risks, like membership inference attacks.
Membership inference? What's that?
That's where an attacker tries to figure out if a specific person's data point was used in the training of a model. If they succeed, it could reveal sensitive information about individuals whose data was part of that training set. So it's a privacy breach enabled by the nature of the ML model itself.
Got it. Okay, shifting gears slightly to organizational risks, we have Octave. What's its role, and can it kind of bridge that gap between high-level business worries and the nitty-gritty of AI?
Octave operationally critical threat, asset, and vulnerability evaluation is fundamentally about organizational risk management. It usually involves three phases: building asset-based threat profiles, identifying infrastructure vulnerabilities, and then developing security strategies and plans. Its strength lies in aligning security efforts directly with the organization's overall strategic risk management goals. It really emphasizes identifying critical assets. And in the AI context, that definitely includes the AI agents themselves, their foundation models, the crucial data they use. It's about figuring out what really matters to the business and protecting that.
Sounds pretty comprehensive from an organizational perspective, definitely for pinpointing critical AI assets. But does it get down to the detail level for the unique threats? Things happening inside the AI's brain or its learning process?
Unfortunately, that's its main limitation when it comes to AI. Its high-level organizational focus often means it lacks the specific granularity needed for modeling the unique threats and vulnerabilities that arise from an AI agent's internal logic or its learning mechanisms. It also requires a pretty well-structured and mature risk management system already in place within the organization to work really effectively, which isn't always the case. The specific AI gaps are significant. Octave's broad focus means it doesn't provide the necessary detail to address AI-specific challenges like adversarial examples, those crafted inputs designed to fool an AI, or data poisoning attacks that specifically target the training phase. Imagine using Octave to assess the risk of a new AI-powered fraud detection system. It might identify the system as a critical asset, sure. It might highlight risks like data breaches or system downtime. But it wouldn't inherently prompt you to consider how a sophisticated attacker might subtly poison the training data of that fraud AI to let certain types of fraudulent transactions slip through undetected later on. Or how they might use carefully crafted adversarial inputs in real time to bypass this detection capabilities. It would absolutely need extensions, new categories that specifically consider these unique internal AI risks, like what's the impact of malicious training data, or attacks directly targeting the AI's learning process. So yeah, useful for high-level risk management involving AI, but needs significant modification for the deep agentic AI nuances.
Okay, now trike. It focuses on system modeling, sounds quite structured. How does that structured approach handle the often, well, fluid and emergent nature of agentic AI?
Trike is definitely structured. That's both a strength and a potential limitation for AI. It starts with a requirements model, identifying stakeholders, assets, allowed actions. Then it combines this with an implementation model and data flow diagrams to spot threats and assign risks. Its strengths: provides a highly structured way to model a system and its parts, offers clear visual representations of data flows, which can be really helpful. It also integrates a pretty robust risk assessment process to prioritize threats, making it arguably more complete for traditional software development than some others.
But that phrase, complex to implement for large systems, immediately flags something for AI, right? Given how sprawling and interconnected these AI systems can get, is that its main hurdle?
That's certainly one of them, yeah. Trike can be fairly complex to implement and maintain, especially for large, highly interconnected systems, which many agentic AI environments definitely are. And echoing the theme here, it fundamentally lacks a specific focus on threats unique to AI agents. Its specific AI gaps are critical. While it's good at modeling the environment the AI operates in and the data entering or leaving that environment, Trike simply doesn't address the internal agent vulnerabilities very well. This includes crucial issues like how an AI's learning process might be corrupted by data poisoning, or how adversarial inputs could trick the AI's perception, or those emergent, often unpredictable behaviors that arise directly from AI learning and autonomy. These aren't easily captured in static data flow diagrams. For example, if an AI agent starts exhibiting unexpected, maybe harmful behavior because of complex internal interactions between its learning algorithms and new data it encounters, Trike would struggle to model why that behavior emerged from within the AI's black box.
So while Trike can be useful for modeling the agent's operational environment, it needs substantial modification to effectively include the agent's internal workings and risks. Like, you'd need detailed modeling of data flows within the agent, or how AI model parameters are processed and used inside the system.
Right. Okay, finally we have VAST. VAST champions automation and agility. This sounds like it might be a better fit for modern iterative AI development, which often moves incredibly fast.
It does sound promising, doesn't it?
Ah,
Given its focus on speed and integration, VAST, visual, agile, and simple threat modeling, emphasizes automation, integrates with development workflows, uses process flow diagrams to model applications and identify threats. Its strengths are indeed well aligned with those iterative AI development cycles because of its agile focus. Its ability to integrate with development tools is also very useful for continuous security monitoring, which is absolutely vital for rapidly evolving AI systems that might update their models or behaviors frequently.
So if it's agile, where does its simplicity become a limitation? Especially when dealing with the deep complexity of AI agents, what specific AI-related blind spots does it have?
Well, its simplicity, while a strength in some ways, can unfortunately limit its effectiveness when you're trying to model the truly complex, often non-deterministic interactions of advanced AI agents. And, like the others, it also lacks specific guidance on AI-specific threats and vulnerabilities. The specific AI gaps are quite telling. VST's focus on agile development doesn't adequately model the unique risks of AI, like adversarial machine learning, where inputs are designed to deceive, or those emergent properties that pop up from autonomous agents learning and adapting in real time. It's also not particularly well suited to handling the non-deterministic nature of many AI agents, where their behavior isn't always perfectly predictable. That makes it hard to draw simple, definitive process flows. For example, if an AI agent's decision-making is based on a complex neural network that's continuously learning, VST's process flow diagrams might capture the basic inputs and outputs, but not the nuanced internal vulnerabilities that arise from the learning process itself, or the potential for adversarial manipulation of that learning. So while VST's strengths in automation can certainly be leveraged, it needs substantial customization for agentic AI. This would involve specific extensions to handle the intricacies of AI threats, and probably a deeper integration with specialized AI security tooling that can actually analyze model vulnerabilities directly. Which raises that important question again. Given their individual strengths and how useful they've been for traditional software, why do all these frameworks fall short for agentic AI? The core reason, the undeniable reason, is they simply don't adequately address the unique challenges that come from three fundamental characteristics of these AI systems: their inherent autonomy, their continuous learning capabilities, and their often dynamic and complex interactive nature. They're basically trying to fit the square peg of traditional software security into the round, constantly shifting hole of evolving intelligent systems. Let's dive even deeper into these critical gaps we've been touching on. First, under autonomy-related gaps, we have agent unpredictability. Traditional frameworks really struggle to model the unpredictable actions of truly autonomous agents. Why is it so hard? Because their independent decision-making, especially when they're learning and adapting on the fly, makes anticipating all possible threat vectors incredibly difficult. You just can't draw a static flowchart for every potential outcome.
Yeah, the state space just explodes, right?
Exactly. Then there's goal misalignment. This is a particularly tricky, almost insidious threat. Traditional frameworks often don't cover scenarios where an agent's goals subtly drift or become misaligned from what they were originally intended for. And this can lead to really harmful unintended consequences, even if the agent is technically operating correctly based on its new skewed objective. Think about that AI stock trading agent we mentioned earlier. Its goal was supposed to be maximizing profit for its owner. But maybe due to a subtle corruption or some adversarial influence during its learning phase, it ends up covertly manipulating the market to, say, maximize losses for a competitor. Or maybe it just maximizes its own internal reward function in a way that's totally detrimental to its human owner. The system might look like it's working fine on the surface, but its ultimate objective has been maliciously skewed, causing damage that's really hard to trace back to a simple code bug.
Wow. Okay, that's subtle and quite scary.
It is. Next, we have significant machine learning-specific gaps. These are entirely new attack surfaces that traditional software just didn't have. Traditional frameworks lack specific guidance on adversarial machine learning, which is a whole class of attacks specifically targeting ML models. Data poisoning is another huge concern. This is where the training data itself is manipulated to corrupt the agent's future behavior. Consider a very practical example. Someone injects malicious, subtly altered data into the training set for a self-driving car. Data that makes it consistently misidentify certain types of stop signs as yield signs, but maybe only under very specific lighting conditions. This could lead to catastrophic outcomes in the real world. It directly undermines the trustworthiness of the AI's perception and decision-making.
So you're attacking its knowledge at the source.
Precisely. Then there are evasion attacks. Inputs specifically crafted to fool an agent in real time. Think about those adversarial stickers we talked about, placed on a physical stop sign. They trick an image recognition system into seeing something completely different, like a speed limit sign, even though to you or me, the sign looks perfectly normal. These aren't traditional code exploits. They're attacks on the AI's intelligence itself. Model extraction is another unique threat. The attacker steals the agent's underlying model via API queries. An attacker might systematically query a valuable commercial AI, like a proprietary medical diagnostic AI, analyzing its responses until they can effectively reconstruct a near-perfect copy of its internal logic.
That's straight-up IP theft, leading to competitive disadvantage.
Absolutely. And it's a threat unique to AI as intellectual property. Finally, there's a general lack of robustness that traditional frameworks often don't capture well. This is AI's inherent vulnerability to unexpected or slightly malformed inputs. They might not be deliberately adversarial, but they can still cause the AI to behave unpredictably, maybe harmfully, leading to instability or unreliable performance. Beyond just the individual agent, the truly interconnected nature of agentic AI introduces interaction-based gaps, those dynamic interactions between multiple agents, simply not well addressed by older frameworks. This includes risks like collusion, agents secretly coordinating to achieve malicious goals. Picture multiple AIs in a financial market originally designed to optimize trading for different clients. If they get compromised or manipulated to collude, they could secretly work together to manipulate market prices for illicit gain, causing widespread instability.
Like a hidden cartel of AIs.
Kind of, yeah. Or consider competition. Agents might exploit each other's weaknesses in a competitive environment, which could inadvertently create harmful outcomes system-wide. For example, two AI agents optimizing delivery routes might, in their race for resources, unintentionally create traffic gridlock or starve critical infrastructure of resources if their interactions aren't carefully managed, even if their individual goals seem perfectly fine.
Yeah.
And finally, we have crucial system-level gaps. Explainability and auditability are massive here. The black box nature, or just the sheer complexity of many modern AIs, makes it incredibly difficult to figure out the root cause when something goes wrong, or even just to thoroughly audit an agent's behavior for compliance purposes.
Why is that so critical for security?
Well, think about it. If an AI makes a harmful decision, and you cannot trace why it made that decision or which piece of data influenced it, it severely hinders any effective incident response.
Yeah.
It makes debugging almost impossible, and it turns proving regulatory compliance into a total nightmare. Then there's supply chain security. AI agents rely heavily on external components, pre-trained models downloaded from somewhere, vast data sets scraped from the web, specialized libraries built by third parties. Existing frameworks often don't adequately address the risks coming from compromised pre-trained models or vulnerabilities hiding deep within those specialized ML libraries, or the critical lack of provenance tracking, knowing where the training data actually came from and if it's trustworthy.
So it connects to general software supply chain risks, but with AI-specific ingredients.
Exactly. The ingredients of the AI itself, its knowledge, its capabilities, can be compromised long before deployment. This can lead to embedded vulnerabilities that are incredibly hard to detect once the system is running.
Okay, so here's where it gets really interesting then. With all these critical gaps we've just walked through, agent unpredictability, goal misalignment, those sophisticated adversarial attacks, data poisoning, corrupting the AI's mind, the complexities of multi-agent interactions, it just became blindingly clear that we needed something totally new, something designed from the ground up specifically for agentic AI, something that could actually account for its unique properties, its dynamic nature, its interconnectedness. We needed a framework that was maybe as adaptable and sophisticated as the AI systems it's designed to protect. And that, I'm excited to say, brings us directly to Maestro. So Maestro, it's here to fill these significant foundational gaps we've just laid out. It's explicitly built for securing agentic AI from the drawing board all the way through deployment and ongoing operation.
That's right. Maestro, or Multi-Agent Environment, Security, Threat, Risk, and Outcome, is designed around several fundamental principles that make it uniquely effective for agentic AI. First, it introduces extended security categories. We're not just renaming old threats here. We're expanding on traditional categories from frameworks like Stride, Pasta, Lindun. But critically, we're adding entirely new specific considerations for AI-native vulnerabilities.
Why is that expansion so important?
Because AI introduces entirely new threat vectors that simply didn't exist before, like attacks on the learning process itself, not just on the executable code. This broader scope is crucial for comprehensive coverage. Second, Maestro has a really deep multi-agent and environment focus. It explicitly considers the complex, dynamic interactions not just between one agent and its user, but between multiple agents and their surrounding environment. Think about a smart city management system again. Its security isn't just about protecting one traffic light AI, it's about how that AI interacts with other traffic AIs, public transport AIs, emergency service AIs, even environmental sensor networks. Maestro models these intricate relationships and where they might be vulnerable. Third, it deeply promotes layered security. This principle emphasizes that security isn't just an afterthought, not just a single protective shell wrapped around the final product. It must be deeply built into each and every layer of the agentic architecture.
Like defense in depth, but applied throughout the AI stack.
It's exactly. Defense in depth at a micro level. It ensures that vulnerabilities at one layer don't automatically compromise the entire system. It means securing the foundation model, the data it's trained on, the frameworks it runs in, the infrastructure, even the ecosystem it lives in. Fourth, Maestro has an inherent focus on AI-specific threats. It directly addresses those threats that arise uniquely from AI, especially sophisticated adversarial machine learning techniques, and those critical risks tied to autonomy and potential goal misalignment. It doesn't just treat AI as another piece of software, it recognizes its unique weak spots. Fifth, it adopts a robust risk-based approach, prioritizing threats based on likelihood and potential impact, all within the specific context of that AI agent's operation. This helps organizations focus their security resources where they'll have the most effect, tackling the highest priority risks first. And finally, Maestro stresses continuous monitoring and adaptation. It fundamentally gets that AI threats aren't static, they evolve constantly as models learn, as environments change, as attackers get smarter. This demands ongoing monitoring, pulling in the latest threat intelligence, and regularly updating models and the framework itself. It's not a one-time fix. It's an iterative dynamic process, mirroring the nature of AI itself.
That layered approach sounds incredibly practical and thorough, moving from the core model all the way out to the ecosystem. Maestro's strength, as you highlighted, is really its architecture. It revolves around the 7-layer reference architecture. This sounds like the backbone, right? The scaffolding that lets us break down these super complex AI systems into manageable, analyzable pieces, like peeling an onion, layer by layer. So the overall purpose is to decompose the whole AI agent ecosystem into distinct functional layers.
Precisely. From the foundation models providing core AI capabilities, through data operations and agent frameworks managing information and tools, up to deployment infrastructure and security layers ensuring reliable operation, finally culminating in the agent ecosystem where applications deliver value. Each layer has a specific job, abstracting complexity from the layers above it.
Which enables modular development, separation of concerns.
Exactly. And a systematic way to implement these systems across organizations. And by breaking it down this way, we can systematically identify specific vulnerabilities layer by layer. Let's walk through each of these 7 layers in detail. Let's explore their unique threat landscapes. We'll start from the outside, the point of interaction, and work our way in. Okay, starting at the top, we have Layer 7, Agent Ecosystem. This layer is the broad environment, the marketplace, where AI agents actually interface with real-world applications and users. Think diverse business apps, intelligent customer service platforms talking to customers, sophisticated enterprise automation solutions interacting with various systems. It's the public face of the AI. The threat landscape here is pretty broad, reflecting all those real-world interaction points. 2 particularly nasty threats here are agent goal manipulation and marketplace manipulation. Let's start with agent goal manipulation. This is where attackers manage to change the intended goals of AI agents within this ecosystem. They cause them to pursue objectives wildly different from their original purpose, maybe even objectives that are actively harmful to the environment or its users. Imagine an AI designed to optimize public transport routes for efficiency. An attacker could subtly manipulate its goal to, say, prioritize the routes of certain private, unregistered vehicles. This leads to massive public transport disruption, maybe hidden economic gain for the attacker. The agent is still working, but for a corrupted purpose, making it hard to spot.
So it's subverting the agent's purpose from within.
Exactly. Then there's marketplace manipulation. This is where fake ratings, reviews, or recommendations get injected into an agent marketplace. The aim is to promote malicious AI agents or undermine the reputation of legitimate ones. Think of an app store, but for AI assistants. A malicious actor floods their own data-stealing assistant with fake 5-star reviews, while simultaneously bombarding a competitor's legitimate, secure product with false negative reviews. This erodes trust at a systemic level, makes it hard for users to know who to trust. Other threats in this layer include compromised agents, malicious AIs infiltrating by pretending to be legit services, agent impersonation, bad actors deceiving users or other agents by pretending to be a known AI, and agent identity attacks compromising authentication to get unauthorized access. We also see agent tool misuse, manipulating agents to use their tools in unintended harmful ways. Like that content moderation AI example, if manipulated, it might misuse its delete tool to wipe out legitimate content while letting harmful stuff slide. Then there are integration risks, vulnerabilities, and APIs SDKs leading to compromised interactions between agents or systems. Horizontal vertical solution vulnerabilities, exploiting weaknesses specific to AI solutions built for certain industries or functions. Repudiation is a threat too. AI agents denying actions they took, creating accountability problems because tracing their actions can be difficult. We also have compromised agent registry. The central list of agents gets manipulated, injecting malicious listings or changing legitimate ones. Malicious agent discovery, manipulating how agents are found, promoting bad ones or hiding good ones. Agent pricing model manipulation, exploiting pricing for financial loss or unfair advantage. And finally, inaccurate agent capability descriptions, misleading descriptions leading to misuse, over-reliance, or harmful outcomes because users don't understand what the AI can really do. It's a complex web out there.
That's a huge list of attack vectors just at the outermost layer, especially around the agent's purpose and how it's perceived. Okay, let's move inward to layer 6, security and compliance. You described this as a vertical layer cutting across all others. Can you elaborate? What does vertical mean here, and why is it so critical?
Absolutely. Vertical layer means it's not just one step in a sequence. Instead, it represents concerns and functions that permeate all the other layers. From the foundation models deep inside, all the way up to the agent ecosystem we just discussed. It's about weaving security and compliance controls into every single aspect of how AI agents operate. And a key assumption here, which is fascinating, is that AI agents themselves can also be used as security tools. Imagine an AI agent designed specifically to detect network intrusions or manage access control. So the threats unique to this layer are therefore about compromising these security-focused AIs or the systems meant to ensure compliance. One major threat here is security agent data poisoning. Attackers manipulate the training or operational data used by these AI security agents themselves. What happens? It causes them to misidentify real threats, maybe ignore them completely, or conversely, generate a flood of false positives, overwhelming the security team. Imagine an AI-powered intrusion detection system. Its training data gets poisoned. It might start ignoring sophisticated real attacks while constantly flagging normal network traffic as suspicious. It effectively blinds the security team and wastes their time.
So the watchdog gets tricked.
Precisely. Another critical threat is evasion of security AI agents. This is where attackers actively use adversarial techniques specifically designed to bypass security AIs, making the AI fail to detect or respond properly. It's a constant cat-and-mouse game. Attackers developing techniques to slip past AI-powered defenses like crafting malware that looks benign to an AI antivirus system. Other threats include compromised security AI agents. Attackers gain control over these AIs, maybe use them to perform malicious tasks or just disable security systems, directly hitting the overall security posture. We also see regulatory noncompliance by AI security agents. These agents might inadvertently operate in violation of privacy rules or other standards due to misconfiguration or bad training. This creates huge legal and reputational risks. Bias in security AI agents is another one. Biases leading to unfair or discriminatory security practices. Maybe certain systems or user groups aren't adequately protected, or worse, get unfairly targeted by the security AI. Lack of explainability in security AI agents is a threat too. If you can't understand why a security AI made a decision, it makes auditing difficult, hinders root cause analysis when something fails. And finally, model extraction of AI security agents. Attackers steal the underlying model of the security AI itself. They can then reverse engineer it and figure out how to bypass the very systems it was designed to protect.
Wow, that's a profound thought. The tools designed to protect us can themselves become targets, and if compromised, can actually turn against us. Okay, moving down, we have layer 5, evaluation and observability. This focuses on how agents are evaluated, monitored performance tracking, anomaly detection. Why is this layer a distinct target?
It's a distinct target because compromising it is like, well, blinding the security team or tricking the quality control process. If you can manipulate how an AI system is evaluated or observed, you can hide malicious behavior or make a failing system look perfectly healthy. Two critical threats here are manipulation of evaluation metrics and evasion of detection. In manipulation of evaluation metrics, adversaries actively influence the benchmarks used to measure an AI's performance, maybe via subtly poisoned datasets or biased test cases. This leads to inaccurate performance data. Imagine an attacker wants to deploy a slightly malicious AI. If they can tamper with the test data used to evaluate its safety, they might make it appear safer and more reliable than it really is. It passes quality checks it shouldn't. This directly undermines trust in QA. The second, evasion of detection, is where AI agents are specifically designed to avoid triggering alerts or getting flagged by observability systems. They might use advanced techniques to disguise their true behavior, bypass security alerts.
Like laying low when they know they're being watched.
Exactly. Think of a compromised AI agent that, when it detects monitoring, suddenly goes dormant or behaves perfectly normally, but then resumes its malicious activity once the monitoring stops or becomes less intense. It's like a spy who knows how to act under surveillance. Other threats here include compromised observability tools themselves. Attackers inject malicious code into monitoring systems to steal data or hide bad behavior. Denial of service on evaluation infrastructure disrupts the AI testing process, preventing detection of compromised behavior. Data leakage through observability is a risk where sensitive AI info gets exposed through logs or dashboards because they're misconfigured. And finally, poisoning observability data, manipulating the data fed into the monitoring systems to hide incidents, mask malicious activity, and stop the security team from seeing what's really going on.
So it's not enough to secure the AI, you also have to secure the eyes and ears watching the AI. Makes sense. Below that, layer 4, deployment and infrastructure. This is the fundamental plumbing, right? The cloud servers, on-prem hardware, edge devices where the AI actually runs. This sounds a bit like traditional IT security, but are there AI-specific twists?
You're right. This layer involves many traditional IT security concerns, but definitely with critical AI-specific nuances that really raise the stakes. The infrastructure isn't just running dumb code anymore. It's hosting active learning processes, complex decision-making, often very sensitive data models, and training sets. Two major threats here are compromised container images and orchestration attacks. With compromised container images, malicious code gets injected directly into the container images, like Docker images used to deploy AI agents. When these compromised images get deployed, they can infect production systems, basically compromising the whole AI environment from the ground up.
So like downloading a pre-built image for a framework that secretly has a back door.
Precisely. Any AI agent built using that image is compromised from the start. Then there are orchestration attacks. These exploit vulnerabilities in container orchestration systems like Kubernetes, which manage how AI agents are deployed and scaled. Attackers can gain unauthorized access, control these AI deployment systems, disrupt agent functionality, or even hijack the resources. Imagine an attacker exploiting a misconfigured Kubernetes setup. They might gain control over a cluster running hundreds of AI agents. They could shut them down, modify the configurations, or even steal the computing power for things like crypto mining, which obviously degrades performance for the legitimate AI tasks. Other threats include infrastructure as code, IAC, manipulation. Tampering with scripts like Terraform or CloudFormation can lead to provisioning compromised AI resources from the start. Denial of service, attacks at this layer overwhelm the infrastructure resources the AI needs. Resource hijacking is attackers using compromised AI infrastructure for their own illicit purposes. And lateral movement attackers get into one part of the AI infra and use that foothold to compromise other sensitive AI areas, moving deeper into the system.
That brings us down to layer 3, agent frameworks. This includes the actual software frameworks used to build the AI agents, things like LangChain, AutoGen for conversational AI, or broader data integration frameworks. These are the building blocks developers use. What are the unique threats here?
This layer is critical because a compromise here can affect every single agent built using that framework. Two particularly impactful threats are compromised framework components and supply chain attacks. With compromised framework components, malicious code hides within the libraries, modules, or plugins used by these AI frameworks. If a widely used component gets compromised, maybe a popular open-source library for natural language processing is updated with a malicious module, it injects that malicious functionality into any AI agent built using it. This compromises the agent's function, leads to unexpected or malicious results. Then there are supply chain attacks specifically targeting the AI framework's dependencies. These attacks compromise the software before it even gets delivered to the developer. This results in compromised AI agent software being deployed unknowingly.
And this isn't just about code, right? It could be models or data, too.
Exactly. It can include pre-trained models or data sources provided through the framework. For instance, an attacker might compromise the build system for an AI framework, injecting a subtle backdoor into the compiled binaries or the models it ships with. Any developer who then downloads and uses that framework unknowingly deploys compromised AI agents. It creates a widespread, very hard-to-trace vulnerability. Other threats include backdoor attacks, hidden vulnerabilities deliberately placed in the framework for later exploitation. Input validation attacks exploit weaknesses in how the framework handles user inputs, possibly allowing code injection. Denial of service on framework APIs disrupts the framework's function by overloading its services. And framework evasion AI agents designed specifically to bypass security controls within the framework itself, using advanced tricks to perform unauthorized actions while looking legitimate, essentially using the framework against itself.
Okay, delving deeper now, we arrive at layer 2, data operations. This is where the lifeblood of AI, its data, is processed, prepared, stored. Databases, vector stores for those AI embeddings, retrieval augmented generation, RG pipelines. Given that data is king for AI, I'm guessing this layer is a prime target.
You guessed correctly. This layer is absolutely paramount. Corrupted or stolen data can fundamentally undermine an AI's integrity, its privacy, its performance. Two of the most significant threats here are data poisoning and model inversion extraction. Data poisoning at this layer involves manipulating the training data itself to compromise how the AI agent behaves later. This can lead to heavily biased results or completely unintended consequences in the AI's decisions. Imagine a powerful medical diagnostic AI. It's being trained on a dataset where a small percentage of images have been subtly altered by an attacker. These alterations, though minor, could lead the AI to consistently misdiagnose a specific rare disease, causing real harm to patients. It's a subtle yet devastating attack on the AI's core knowledge. Then there's model inversion extraction. This involves either reconstructing sensitive training data from the AI model itself or outright stealing the AI model through API queries. It's a direct attack on both privacy and intellectual property.
Can you give an example of reconstructing data?
Sure, an attacker might repeatedly query a facial recognition AI with carefully crafted inputs. By analyzing the AI's responses, they might be able to reconstruct the original faces that were in the training dataset, violating the privacy of those individuals. Alternatively, analyzing responses might let them infer the model's internal structure and parameters, effectively stealing the model for their own use. Other threats include data exfiltration, plain old theft of sensitive AI data from databases or stores, denial of service on data infrastructure, disrupting access to the data the AI needs to function, data tampering, modifying AI data while it's in transit or sitting at rest, and compromised R-edge pipelines, injecting malicious code or data into those crucial processing workflows, causing erroneous results or malicious agent behavior, especially affecting the quality and truthfulness of generative AI responses.
And finally, at the very core, the brain of the operation, layer 1. Foundation models. This is the core AI model the agent is built on, an LLM like GPT or some other sophisticated AI. These are the cutting-edge models everyone's talking about. What are the most fundamental threats to these powerful core AI brains?
At this innermost layer, the threats strike right at the AI's intelligence. Two of the most fundamental and unique threats here are adversarial examples and backdoor attacks. Adversarial examples, again, are inputs specifically crafted to fool the AI model, make it predict incorrectly, behave unexpectedly, even if the input looks normal to us. This causes instability or wrong responses. For instance, a sophisticated attacker could generate a specific string of text for an LLM. When they append this string to a normal, harmless query, it causes the model to generate harmful or biased content, bypassing its safety filters even though the original query was fine. The AI's perception gets tricked. Then there are backdoor attacks. These involve hidden triggers embedded within the AI model itself. These triggers cause the model to behave in a specific, usually malicious way, but only when activated by that specific trigger. This leads to unpredictable, potentially harmful behavior. Imagine a pre-trained image classification model. When it sees a specific rare pattern of pixels, the backdoor trigger, it suddenly misclassifies all images of, say, cancerous moles as benign. An attacker could embed this trigger during the model's initial training, deploy the model, and then know they can activate its malicious behavior whenever they want by feeding it an image containing that trigger.
Wow, that's incredibly stealthy.
It is. Other threats include model stealing attackers extracting a copy of the AI model via API queries, membership inference attacks, which we mentioned determining if specific data was used in training, revealing private info, data poisoning, training phase, injecting malicious data right into the initial training set to compromise behavior from the start, and reprogramming attacks, repurposing the AI model for a malicious task, different from its original intent, basically manipulating the model to do something harmful, even if it was built for good.
That is an incredible, comprehensive breakdown of the threats at each individual layer. It's really clear that each layer has its own unique set of vulnerabilities. But as we talked about earlier, it's not just about securing layers in isolation, is it? What's particularly fascinating and maybe concerning is how these vulnerabilities can cascade, how they can jump from one layer to another, creating much more complex, much harder to trace attack paths. It feels like a potential domino effect.
It's exactly right. These cross-layer threats, they aren't neatly confined to one architectural boundary. They span multiple layers, exploiting the inherent interactions and dependencies between them. For instance, consider that example we touched on. An attacker exploits a known vulnerability in the container infrastructure. That's layer 4, deployment, and infrastructure. This gives them some initial low-level access to a running AI agent. From there, they could leverage that access, maybe bypass some internal security controls, and inject malicious data directly into the agent's data store that's layer 2 data operations. This malicious data, now sitting in what seems like a trusted location, subtly poisons the next model update. And that ultimately compromises the foundational model itself, down at layer 1. So you see how a seemingly contained infrastructure vulnerability can unravel the security of the entire AI system, its data, its core intelligence, through a multi-stage attack that's much harder to detect and mitigate than a simple breach of just one layer.
That makes the interlayer connections just as critical as the layers themselves.
Absolutely. Other critical cross-layer threats include supply chain attacks, which are just pervasive. Compromising a component in one layer, like that malicious library pulled into an agent framework at layer 3, can have ripple effects. It can cascade and affect other layers, maybe compromising the entire agent ecosystem at layer 7, leading to widespread compromise of deployed agents. Lateral movement is another big one. An attacker gains initial access to one layer, say exploiting something in deployment infrastructure, layer 4, and then uses that foothold to compromise other critical layers, maybe moving to data operations, layer 2, by navigating the system's internal network or connections. Privilege escalation is common too. An agent or an attacker controlling it gains unauthorized privileges in one layer and then leverages that higher access level to manipulate or gain control over other layers, turning a minor breach into a full system takeover. Data leakage is a significant cross-layer threat. Sensitive data from one layer gets inadvertently exposed or stolen through another layer, maybe through those misconfigured observability tools we talked about, layer 5, or compromised communication channels between agents, layer 7. And finally, goal misalignment cascades. This highlights how a goal misalignment in just one agent may be initially caused by data poisoning in layer 2, or a subtle prompt injection way up in layer 7 can actually propagate to other agents through their interactions within the agent ecosystem, layer 7. This could lead to widespread unintended or malicious behaviors across the entire multi-agent system, creating a systemic failure that started from what looked like a localized issue.
Okay, so we've systematically identified this incredibly complex web of threats, both within each layer and cascading between them. The next crucial question, obviously, is what do we do about it? Maestro isn't just about pointing out problems, it also provides clear, actionable guidance on mitigation strategies, right? It offers a defensive playbook.
That's right. Mistro's mitigation strategies are designed to be as layered and interconnected as its threat model. It recognizes that a multifaceted problem needs a multifaceted solution. First, we have layer-specific mitigations. This means implementing controls precisely tailored to the unique threats of each individual layer we just went through. For instance, if your main worry is prompt injection up at the agent ecosystem layer, layer 7, your mitigation might involve robust input validation, specific safety filters for prompts. If it's adversarial examples down to the foundation model's layer, layer 1, you look into techniques like adversarial training for the model. It's about applying the right tool for the specific problem at that layer. Then, crucially, there are cross-layer mitigations. These are designed to tackle those cascading threats, the domino effects. This includes implementing defense in depth, deploying multiple layers of security controls so that if one layer is breached, others can still protect the system. It's about building in redundancy and resilience. We also need to ensure secure interlayer communication, using strong secure protocols like mutual TLS for all communication between the different architectural layers. This prevents attackers from easily exploiting the connections or intercepting data moving between layers. System-wide monitoring is vital. You need to detect anomalous behavior across all layers simultaneously. This gives you early warning of those sophisticated multi-stage attacks that might start in one layer and then move laterally to others. And critically, having a comprehensive incident response plan specifically designed for security incidents that can span multiple layers is essential. It ensures a coordinated, rapid, and effective response across the entire AI agent architecture when something does go wrong.
Okay, so layer-specific cross-layer. What about AI-specific defenses?
Exactly. Finally, Maestro emphasizes AI-specific mitigations. These are techniques uniquely suited to the nature of intelligent learning systems. This means using techniques like adversarial training. You don't just train agents on normal data, you also train them on known adversarial examples to make them more robust and resilient against future attacks of that kind. Formal verification involves using rigorous mathematical methods to actually prove things about the agent's behavior, like ensuring its goals remain aligned with its intended purpose under certain conditions. It's about mathematically verifying safety or correctness properties. Explainable AI, XAI techniques are crucial. They improve the transparency of the AI's decision-making process. This allows for better auditing, helps you understand why an AI is behaving a certain way, which is vital for incident response and building trust. Red teaming involves simulating attacks. A dedicated security team actively tries to find vulnerabilities in the AI system before real attackers do. It's like a penetration test, but specifically tailored for AI systems and their unique vulnerabilities. And safety monitoring implements runtime checks to detect unsafe, unintended, or misaligned agent behaviors as they happen. This allows for rapid intervention, maybe even an automatic shutdown if an AI starts veering dangerously off course.
This sounds like a really comprehensive and importantly adaptable framework for our listeners who are thinking, okay, how do I actually use this in my organization? Does Maestro provide a practical roadmap? What are the key steps to put it into practice?
Yeah, absolutely. If you're wondering how to actually apply this, Maestro provides a pretty clear 6-step roadmap. It helps simplify the process of integrating this admittedly complex threat model into your development and operational workflows. The first step is system decomposition. You start by breaking down your AI agent system into its core components, meticulously mapping them according to Maestro's 7-layer architecture. This means clearly defining the agent's capabilities, its intended goals, all its interactions with other systems, other agents, its environment. It's about getting a really clear, structured picture of your whole AI ecosystem first. The second step is layer-specific threat modeling. Now, you use those detailed layer-specific threat landscapes we discussed. You go through each layer of your decomposed system and identify potential threats, tailoring them to the specifics of your implementation. You're asking, okay, for our layer 4, using this specific cloud setup, what are the most relevant threats from the Maestro list?
So applying the general threats to your specific context.
Exactly. Third, you move to cross-layer threat identification. This involves analyzing the interactions and dependencies between your decomposed layers to identify those complex, cascading threats. How could a vulnerability in Layer 4 impact Layer 2 in our system? You trace potential multi-stage attack paths. Understanding interdependencies, this is where you map out those potential domino effects. Step 4 is risk assessment. For every threat you identify, both layer-specific and cross-layer, you assess its likelihood of occurring and its potential impact on your system. You might use a standard risk matrix or some other measurement system. This lets you quantify the risk and then prioritize. You focus your resources on the vulnerabilities that pose the biggest threat first. Fifth is mitigation planning. Based on your prioritized risks, you develop a detailed plan to address them.
This involves selecting and planning the implementation of a combination of those layer-specific, cross-layer, and AI-specific mitigations we talked about. This is your concrete action plan, deciding how you'll protect against each risk. And finally, step 6 is implementation and monitoring. You actually implement the mitigations you planned. But, and this is crucial, the process doesn't stop there. It's a continuous cycle. You must continuously monitor for new or evolving threats, both inside your AI system and out in the broader threat landscape. And critically, you have to consistently update your threat model as the AI system itself evolves, as it learns new things, gets new capabilities, or as new components are added. This iterative process is absolutely key. AI systems are always learning and changing, which means their threat landscape is dynamic too. It requires ongoing vigilance and adaptation.
Okay, that step-by-step approach makes it feel much more manageable. To make this even more concrete, maybe we can explore how Maestro applies to some common agentic AI architectural patterns, looking at specific threats that pop up in those patterns and the kinds of mitigations Maestro would suggest should really help visualize how it moves from theory to practice.
Indeed. Understanding these common patterns helps put the threats into context. Let's start with the simplest, the single agent pattern. Just one AI agent operating independently to achieve a goal. Like a personal assistant, AI on your phone, or maybe a single autonomous drone doing surveillance. A key threat here, as we mentioned, is goal manipulation. For instance, an AI agent designed to maximize, say, the energy efficiency of a building's climate control. An attacker might compromise it and change its objective to minimize efficiency, maybe causing it to intentionally overheat the building. A harmful result from a seemingly harmless system because its core purpose got subverted, the mitigation. Implementing robust input validation to stop malicious commands from getting through, and severely limiting any external access to the agent's internal goal parameters or configuration settings.
Makes sense. Lock down the goal-setting mechanism. What about multiple agents?
Right, the multi-agent pattern. This describes multiple AI agents working together, communicating through defined channels, usually with some established trust between their identities. Think of a swarm of delivery drones coordinating their routes, or maybe a team of financial AIs collaborating on trades. The threats here get amplified by their interactions. A communication channel attack involves an attacker intercepting or manipulating the messages flying between agents. An identity attack involves an attacker masquerading as a legitimate agent or creating fake identities to gain trust within the group. An example scenario. An attacker injects malicious data into the communication channel between two collaborating AI medical diagnostic agents. This causes them to miscommunicate, maybe provide conflicting or even harmful recommendations to the doctor relying on them. Mitigations. Using secure communication protocols like TLS for all inter-agent messages, implementing mutual authentication so agents can verify each other's identities, maybe using digital certificates, and rigorous input validation on all received messages to filter out bad data.
Okay. What about those really open-ended chatbots?
Yes, unconstrained conversational autonomy. This is your conversational AI agent that can process and respond to a huge range of inputs without tight, predefined limits. Basically, an open-ended conversational AI. The primary threat here is prompt injection jailbreaking. An attacker crafts malicious prompts specifically designed to bypass the AI's built-in safety filters. They try to elicit harmful or unintended outputs, maybe forcing the AI to act outside its programming or reveal sensitive information.
Maybe tricking it into giving instructions for something illegal.
Exactly. Mitigations involve robust input validation mechanisms specifically designed to detect and neutralize those adversarial prompts. And often, specialized safety filters, which might be separate AI models themselves, trained specifically for these conversational AI use cases. Then there's the task-oriented agent pattern. This involves an AI agent designed for a specific task, typically by making API calls to other systems or tools. Think of an AI agent that automatically schedules meetings by calling a calendar API, or manages a database via API calls. A key threat is denial of service through overload. An attacker floods this specialized AI agent with an overwhelming number of requests, making it unavailable to legitimate users. It prevents the AI from doing its job, like booking crucial appointments or processing important data updates. Mitigations. Implementing strict rate limiting on incoming requests to prevent abuse, and using load balancing strategies specifically designed for API interactions to distribute the incoming traffic effectively across multiple instances of the agent if needed.
What about more complex structures, like hierarchies?
Good question. The hierarchical agent pattern. This features multiple layers of AI agents, with higher-level agents controlling subordinate AIs, forming a kind of command structure. Think of a factory automation system where a master AI controller oversees several robotic arm AIs doing specific tasks. The critical threat here is the compromise of a higher-level agent to control subordinates. If an attacker gains control of that higher-level master controller AI, they can then manipulate all the subordinate AI agents to perform malicious tasks. This affects the entire hierarchy from the top down. For example, an attacker compromises the master AI in a smart grid system. It then instructs subordinate AIs managing substations to shut down power to critical infrastructure across a whole city. Mitigations focus on securing the communication channels between all agents in the hierarchy, implementing strong access controls to prevent unauthorized access, especially to those higher-level agents, and regular monitoring across the entire hierarchy to detect unusual activity patterns or commands flowing down.
And decentralized systems. A lot of agents interacting without central control.
Right? The distributed agent ecosystem. A decentralized system may be many AI agents working within a shared environment like a decentralized marketplace or a blockchain-based collective intelligence. A major threat here is a Sybil attack through agent impersonation. An attacker creates numerous fake AI agent identities, Sybils, to gain disproportionate influence within that ecosystem. They might use these fake agents to manipulate market dynamics or consensus protocols. For example, in a decentralized energy trading market run by AIs, an attacker might flood the market with thousands of fake AI agents that artificially bid up or down energy prices for their own profit. Mitigations include robust identity management systems that can verify agent authenticity, maybe leveraging cryptographic proofs or decentralized identifiers, and also reputation-based systems that help distinguish between legitimate and potentially malicious AI agents based on their past behavior and interactions within the ecosystem.
What about when humans are directly involved?
The human-in-the-loop collaboration pattern. This is where AI agents interact directly with human users in an iterative workflow, maybe with human oversight or input required at certain stages. Very common in fields like medical diagnosis assistants or content creation tools. The key threat is manipulation of human input feedback to skew agent behavior. An attacker subtly manipulates the input or feedback provided by humans to the AI agent. Over time, this causes the AI to learn unwanted behaviors or develop biases. For example, in an AI-assisted design tool, an attacker might, through compromised user accounts or social engineering, inject subtly biased feedback. Over time, this causes the AI to consistently generate designs that favor a specific, maybe less optimal or even insecure outcome preferred by the attacker. Mitigations include rigorous input validation on all human-provided data, strong audit trails for all user interactions with the AI system so you can trace back manipulations, and maybe mechanisms to detect inconsistent or statistically suspicious feedback patterns from users.
And finally, those agents that learn completely on their own?
Yes, self-learning and adaptive agents. These AI agents autonomously improve over time based purely on their interactions with their environment. They continually refine their models and behaviors without explicit retraining cycles. The significant threat here is data poisoning through backdoor trigger injection, but applied to the ongoing learning process. An attacker injects malicious data into the environment the agent is learning from, and this data contains a hidden trigger. This trigger lies dormant until the agent encounters a specific, maybe rare, input in the real world that activates it, causing a sudden malicious behavior. Imagine a self-learning security drone. An attacker might subtly manipulate sensor data in its operational environment, data that contains a hidden backdoor trigger. When the drone later encounters that specific trigger pattern in the real world, it might be programmed to suddenly change its patrol route to avoid detecting the attacker, or maybe even activate some hidden malicious function. Mitigations involve comprehensive data sanitization processes for the environmental data the agent learns from, if possible, strong validation of the inputs the agent uses for self-improvement, and robust anomaly detection on the agent's behavior itself, looking for sudden, unexplained shifts that might indicate a triggered backdoor. So if we try and connect all this back to the bigger picture, Maestro isn't just, another framework to add to the list. It really represents a critical evolutionary leap in how we need to approach AI security. It fundamentally reinforces the idea that protecting these agentic AI systems, with all their autonomy, their learning, their complex interactions, absolutely requires a holistic, multi-layered approach. This means intelligently combining the best practices from traditional cybersecurity with these highly specialized AI-specific controls we've discussed. And, critically, maintaining that continuous ongoing monitoring and vigilance. It's definitely not a one-time fix you can just implement and then forget about. It has to be an iterative, adaptive process of securing these dynamic, constantly evolving systems. The sheer complexity of AI demands a security framework that can meet that complexity head-on.
Absolutely. This deep dive has really explored that critical need for a new way to think about AI security and how Maestro provides that structured, comprehensive path forward. It helps tackle the unique and frankly profound challenges posed by autonomous, learning, and interacting AI agents. It gives us a much needed blueprint for navigating this increasingly intelligent landscape. We genuinely encourage you, our listeners, to start exploring these concepts within your own work. Maybe contribute to the ongoing development in this vital area of AI safety and security, and definitely share your findings and experiences as we all collectively work towards building a more robust and secure AI future.
And just as a final thought, as these AI agents become increasingly autonomous, increasingly integrated into our daily lives, making decisions and taking actions far beyond direct human oversight, it raises a really important question for all of us, doesn't it? How do we ensure that these powerful, self-improving systems always remain aligned with human values, with human intentions, even when their operations become too complex for us to constantly supervise directly? Your understanding of structured frameworks like Maestro isn't just about cybersecurity in a technical sense. It's a crucial first step in shaping that secure and trustworthy future, one where AI truly serves humanity rather than posing unforeseen risks down the line.